Iron, the most useful of all metals. Everywhere we look, we see iron. Its services to mankind are limitless. Iron is the basis of innumerable forms of metal. In one form, it is used where strength is required. In another, beauty is an important factor. Iron is used in beams that must be rigid, as well as in structures that are springy and elastic. Iron where there is great strain or where hardness is needed. Some forms of iron resist long exposure to the elements. Others are unaffected by heat. The most common commercial source of iron is iron ore. Iron which is found in the Earth's interior in the form of a red dust that is one of man's most valuable possessions. Huge masses of this ore are transported from the mines to the blast furnaces. In the blast furnace, the process of changing the iron ore into iron is carried out on a tremendous scale. The iron ore is mixed with coke and limestone and then loaded into the top of the furnace. This towering structure holds many, many tons of the red ore, which is soon to become iron. A blast of superheated air forced into the furnace sweeps up through the raw materials. The air heats the coke until it burns at white heat. The heat drives most of the impurities from the iron ore, leaving liquid iron in a pool at the bottom of the furnace. In the laboratory, we can see how the ore is converted into iron. The ore is mixed with a powdered chemical. When the mixture is ignited, it burns at terrific heat. The impurities are driven off, leaving white-hot molten iron. In the blast furnace, the molten iron contains some other elements which have been soaked up during the process. So the molten metal is usually transported in its liquid state directly to the steel mill. In the mill, many huge furnaces await the carloads of dazzling liquid iron. The iron is poured into the flaming furnaces where most of the impurities are burned out. The process of removing the impurities changes the iron into steel. The steel is drawn from the furnace and poured into molds, forming ingots. The molds are stripped off the ingots after the steel is hardened. The huge blocks of steel, weighing several tons, are placed in a soaking pit or open furnace and reheated to uniform temperature. When the ingots are white hot, they are taken out of the soaking pits and transferred to the blooming mills. In the blooming mills, the ingots are shaped and pressed by powerful rolls. The massive rolls exert terrific pressure on the hot steel, kneading it and flattening it until at last it can be worked into almost any desired shape and thickness. Steel is strong, hard, enduring. But the strenuous use to which steel is put today demands many special characteristics. More different kinds of steel are needed to meet the high manufacturing and engineering standards of the automobile makers than for any other purpose. And so, the modern automobile makers have laboratories for testing and improving the qualities of steel. In the laboratory furnace, we see how steel can be given special characteristics by mixing with it small amounts of other metals. Steel can be made extremely hard by adding a small amount of chromium. The chromium is added to the melted steel. After careful blending, the mixture is poured into a mold and then scientifically brought to normal room temperature. The hardness of steel to which chromium has been added is measured by denting it. A small, extremely hard ball is forced down into the steel test specimen. The size of the dent or impression is measured under the microscope. The smaller the dent, the harder the steel. A microscope isn't needed to compare the size of the dents made in hard chromium steel and ordinary steel. Some uses of steel require it to be extremely strong, able to withstand tremendous strains. The strength of metals is measured by pulling test pieces apart in a powerful machine. The dial of the testing machine shows the tremendous force used in pulling apart a piece of plain steel. More and more force is used. The steel stretches under the load and then finally snaps. More than 13,000 pounds of force are required. Plain steel can be made stronger by adding nickel, in addition to a small amount of chromium. Now let's see what happens when the chromium nickel steel is tested in the stretching machine. The bar breaks. Our chromium nickel steel test piece is more than twice as strong as common steel. Great heat weakens common steel, but some steels today have to stand up under great heat and still keep all their good qualities. Steel can be given an ability to resist great heat by the addition of a little chromium and also some silicon, the element which is found in ordinary white sand. Under constant bending or vibration, all ordinary steels have a tendency to become fatigued or tired. In the laboratory, the fatigue strength of metals is measured by placing a test bar in a machine, which in a short time duplicates the effect of years of use. By adding a little bit of nickel and a small amount of a metal called molybdenum, plain steel can be made to stand up for years and be practically tireless. For certain conditions, a steel is needed that will be very hard on the outside and tough on the inside. A little carbon added to the outside of steel gives it a hard surface and leaves the inside tough and strong. This process is called carburizing or case hardening. By special photography, we can see what happens to a piece of steel when it is completely surrounded by small particles of carbon-bearing material. When heated, the steel slowly soaks up the carbon to form an extremely hard surface. This adding, mixing, and combining of plain steel with friendly little fractions of other metals to improve its qualities is called alloying. Chromium, nickel, silicon, molybdenum and vanadium, tungsten and manganese. All these tough friends have improved the usefulness of steel. But all of these different alloy steels must be put through a process called heat treating. The alloy steel is heated very carefully, heated until it glows, and then quenched or cooled quickly in oil or water. The steel is then reheated at a lower temperature. This is called drawing or tempering. The heat treatment brings out all of the good qualities of each of the alloy steels. The complete motor car has more than 4,500 different parts, for each of which we must select the best metal to give us the finest performance and the greatest dependability with safety and long life. For swift cooling of the ribbed brake drums of perfected hydraulic brakes, cast iron is used. Top sheets of carbon steel are pressed into sturdy turret tops and unisteel bodies. Rigid girders, capable of resisting all sorts of shocks and strains, are formed of specially treated steel for rugged box girder frames. Steel with chromium added for hardness is pounded and cut and polished into gears for the silent transmission of power from engines to rear wheels. Chrome nickel steel, steel made stronger by alloying it with two tough friends, goes into axle shafts that will stand up under twisting strains. Modern shockless steering is made safer by the same tough chrome nickel alloy. Large valves made of chromium and silicon steel resist temperatures over 4,000 degrees in high compression valve and head engines of today. Silicon and manganese make springs more elastic and durable and improve the effectiveness and long life of knee action units. Carbon, added in the case hardening process, gives rugged, wear-resisting hypoid rear axles and makes possible the low center drive. Over 80 different alloy steels, especially for use in the motor car of today, have been developed from the one basic building block, iron. And each of these steels is the best for its particular use in its particular place. There are strong steels, hard steels, tough steels, heat-resisting steels, stainless steels, all to give the motorist the utmost in performance, economy, safety, and long life in his motor car.